Welcome to Section 8.1, Part 1. This is the 61st session of the CISSP Exam Prep series. In this session, we'll start building secure systems from the ground up. We'll answer several questions. Why should security be part of design from day one? Who or what is a subject, and what is an object? What makes transitive trust dangerous? How do open and closed systems differ? And why should you never trust default settings? Why does this matter beyond the exam? Because you rarely inherit a clean slate. Picture a team shipping a new patient scheduling app, wiring it into a cloud vendor, and reusing an old payment library. Every one of those choices bakes in security, or fails to. When you understand secure design, you catch weak assumptions during architecture reviews before they harden into expensive rework. So why should security be part of design from day one? Because retrofitting protection is slow, costly, and leaky. Bolting locks onto a finished building never fits as well as designing them in. Modern Secure by Design guidance pushes 3 ideas. First, own your customer's security outcomes, so products ship safe out of the box. Second, be radically transparent about flaws, sharing what you learn so the whole community improves. Third, drive security from the top, with leaders accountable for it during development. Security becomes a business goal, not a late patch. Who or what is a subject, and what is an object? Every access request has 2 sides. The subject is the active side that asks for access. That is often a user, but it can also be a process, a service, or even a whole organization. The object is the passive side being requested, like a file, a printer, or a database. Here is the twist. These roles are not fixed. A service that is the object of one request can turn around and become the subject of the next. Think of a relay runner who receives the baton, then hands it on. The same entity plays both parts. What makes transitive trust dangerous? Transitive trust is the chain where if A trusts B and B trusts C, then A quietly ends up trusting C. It behaves like simple math. If A equals B and B equals C, then A equals C. The problem is that A never vetted C directly. Say a company blocks a distracting website to keep staff focused. A worker who cannot reach it directly connects to an outside proxy or VPN, and that service reaches the blocked site on their behalf. The block is bypassed through the middleman. Anytime you allow a bridge, you may inherit everything on the far side of it. How do open and closed systems differ? A closed system is built to work mostly with gear from one maker, using private specifications that are not published. An open system follows shared industry standards, so it plugs into products from many vendors through common interfaces or APIs. An API is just an agreed set of rules for how software components request things and exchange data. Open systems are far easier to connect, which is exactly why they draw more attackers. Their standard parts create predictable entry points, and there is a huge shared body of knowledge on how to break them. A closed system is harder to attack, simply because an intruder must first learn its unfamiliar internals. Openness buys interoperability, but it demands stronger defensive coding and layered defense to stay safe. Is open source the same as an open system? No, and mixing them up will cost you exam points. Open versus closed system is about integration and standards. Open versus closed source is about whether the internal code is visible to the public. Open source code invites public inspection to improve it over time. Closed source code leans on the vendor to fix and revise it. Any combination is possible. A closed source program can run as an open system, and open source code can run as a closed system. Read every question slowly, because these terms sit one word apart. Why should you never trust default settings? Because defaults are chosen to make installation painless, not to make you secure. Vendors pick settings that minimize support calls, which is why so many devices ship with a known default password. That convenience is a gift to attackers, who scan for exactly those factory settings. Treat every default as the worst possible option for your environment, then review each one deliberately. A lockdown configuration is less friendly and does less out of the box, but that friction is the point. If you build products, document every setting so customers can harden intelligently instead of guessing. So let's bring it together. Security belongs in design from the very first stage, driven from the top and shipped safe by default. Access always involves a subject and an object, and those roles can swap between requests. Transitive trust lets risks sneak in through a trusted middleman. Open systems trade easy integration for a larger attack surface. And open source is a separate idea about visible code. And defaults are built for convenience, so you must review and restrict them yourself. Get these foundations right, and every control you add later lands on solid ground. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 8.1, Part 2. This is the 60-second session of the CISSP Exam Prep series. This part continues our tour of secure design principles. In this session, we'll cover how systems should behave when things go wrong and why simpler is safer. We'll answer several questions. What does it mean to fail securely? How do you handle errors and bad input gracefully? What is the difference between fail-safe and fail-secure? How do those terms flip between the physical and digital worlds? Why does simplicity make a system easier to protect? And how does explainable AI extend that idea? Why does this matter beyond the exam? Because failure is not a maybe, it is a when. Imagine a badge reader at a data center loses power during a storm. Whether those doors spring open or slam shut is a design decision someone made long ago. On the job, you are often the person asked to make that call, and getting it wrong can trap people or expose assets. Thinking clearly about failure and simplicity is daily engineering, not theory. So what does it mean to fail securely? It means a system is designed ahead of time to land in a safe, predictable state when something breaks. Failure can come from countless causes, but what matters is how the system responds. A program only fails securely because a developer planned for it. Think of an aircraft that is engineered so that even a hydraulic loss still leaves the pilot able to land. The safe outcome is not luck. It was built in. How do you handle errors and bad input gracefully? You start with error handling, sometimes called exception handling. That is code written to anticipate problems and deal with them before they crash the program. Many languages offer a try-catch structure. You place risky code in the try branch and recovery code in the catch branch, so an error is caught instead of fatal. Then you guard the front door with input validation. You check user input for length, filter out known bad patterns, and neutralize dangerous characters. Picture a bouncer who inspects every guest before the door, rather than chasing troublemakers once they are already inside. What is the difference between fail-safe and fail-secure? Both describe a complete failure, but they protect different things. Before that, note the gentler option, fail-soft. To fail soft is to let a system keep running after one component dies, like a multitasking computer where one crashed app does not take down the others. When full failure is unavoidable, you must choose a priority. Fail-safe protects people first. A fail-safe door unlocks in an emergency so everyone can escape. Fail-secure protects assets first. A fail-secure vault door locks itself down when an alarm trips, even if that inconveniences whoever is nearby. One saves lives, the other saves valuables. How do those terms flip between the physical and digital worlds? Context changes their meaning, so pin down which world you are in. In the physical world, a fail-open response leans toward availability and goes by the name fail-safe, while a fail-closed response leans toward protection and goes by the name fail-secure. In the digital world, the focus shifts to the core triad. Fail-open keeps a connection flowing to protect availability, the way a firewall might pass traffic unfiltered if it crashes. Fail-closed cuts the connection to protect confidentiality and integrity, blocking all traffic instead. When an operating system hits a memory isolation violation and halts into a stop error, that is failing closed on purpose. Always ask first, physical or digital, before you translate the term. Why does simplicity make a system easier to protect? Because complexity is where security goes to hide and break. This is the keep it simple and small principle. More lines of code mean more to test. More parts mean more places to fail. More features mean a larger attack surface. Related ideas reinforce it. Do not repeat yourself, so a fix lands in one place. Build only what you actually need right now, not every feature you can imagine. Use the least powerful tool that solves the problem. Think of a Swiss Army knife with 40 blades. Half of them just add ways to cut yourself. A lean design is easier to secure, troubleshoot, and verify. How does explainable AI extend that idea? It carries simplicity into the world of machine learning. A black box model that no human can interpret is a security risk, because hidden logic can conceal bias, flaws, or tampering. Explainable AI adds transparency, letting you trace how a given input produced a given output. Interpretable models go further, staying understandable by design. Guidance like the NIST AI risk management framework stresses systems that are reliable, accountable, and transparent. Think of a chef who lists every ingredient on the menu, so no hidden allergens slips through. Visibility is what lets you actually assess the risk. So let's bring it together. Failing securely means designing the safe landing before the crash, using error handling and input validation to stay in control. Fail-safe protects people, fail-secure protects assets, and those labels flip meaning between the physical and digital worlds, so always check context. Simplicity shrinks the attack surface and makes everything easier to secure and verify. An explainable AI pushes that same transparency into modern models, designed for the bad day, and keep it lean. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 8.1, Part 3. This is the 63rd session of the CISSP Exam Prep series. This part finishes our set of secure design principles. In this session, we'll rethink where trust lives in a modern network. We'll answer several questions. What is zero trust? And why did the old perimeter fail? How does microsegmentation contain a breach? When is total isolation the right call? How does trust but verify compare, and which one wins today? What is privacy by design? And what problem does Secure Access Service Edge solve? Why does this matter beyond the exam? Because the old idea of a hard shell around a soft interior no longer fits reality. Picture a laptop that works inside the office, then at a coffee shop, then back at a client site, all in one day. There is no clean inside or outside anymore. As an architect, you are the one deciding how to secure identities and data when the perimeter has effectively dissolved. These principles are how you do that. So what is zero trust? And why did the old perimeter fail? Zero trust means nothing, and no one is trusted automatically, inside or out. The old model assumed everything inside the network was safe, which crumbled the moment an insider went rogue or an attacker slipped past the edge and roamed freely. With mobile devices and cloud services, the line between inside and outside barely exists. Zero trust flips the assumption to never trust, always verify, and it assumes a breach has already happened. Every single request must be authenticated, authorized, and encrypted before access is granted. Think of an office where your badge is checked at every single door, not just the front lobby. How does microsegmentation contain a breach? It slices the internal network into many small, walled-off zones. Each zone is separated by internal firewalls, subnets, or virtual LANs. And a zone can be as small as one high-value server. Traffic between zones is filtered, often forced to authenticate, and usually encrypted. The payoff is that a breach in one zone cannot spread sideways across the whole environment. This is what stops lateral movement. So an intruder who lands in one corner stays stuck there. Picture a ship built with watertight compartments. One flooded room does not sink the vessel. When is total isolation the right call? Sometimes filtering is not enough, and you need to cut a system off completely. That is an air gap, where a machine has no wired and no wireless link to any other system. It physically severs the network path. Because wireless signals are everywhere, enforcing a real air gap can even require shielding, like a Faraday cage, to block stray radio. Think of a sealed vault with no doors, windows, or phone lines. You reserve this for the most sensitive systems, because the isolation that protects them also makes them hard to use. How does trust but verify compare, and which one wins today? Trust but verify is the older approach, where anyone inside the security perimeter is trusted after an initial login, then largely left alone. The problem is obvious. That standing trust is exactly what lets insiders abuse access and lets intruders move laterally once they are in. Given how fast threats evolve, a single check at the door no longer holds. So when the exam asks, zero trust or trust but verify, the modern answer is zero trust. Continuous verification beats a one-time handshake. What is privacy by design? It is the practice of building privacy protections into a product from the very start, rather than tacking them on at the end. It mirrors security by design, treating privacy as a core part of the architecture across the whole software development lifecycle. Its foundational principles push you to be proactive, not reactive, to make privacy the default setting, and to protect data across its entire lifecycle with real transparency and respect for the user. The whole point is prevention. Stop the privacy violation before it can happen. Think of designing a house with curtains already fitted on every window, instead of scrambling for cover after the neighbors complain. What problem does Secure Access Service Edge solve? It answers the reality of a cloud-based, work-from-anywhere world. Secure Access Service Edge, often shortened to SASE, merges network security functions with wide-area networking into one cloud-delivered service. Instead of hauling all traffic back to a central office, it pushes security and networking out to the edge, close to users, which cuts latency. Its core is identity-centric. It leans on zero-trust network access, so every user and device must authenticate and be authorized, with multi-factor authentication for users wherever possible. It also monitors behavior continuously and adapts in real time. Think of a security guard who travels with you rather than sitting at one fixed gate you must always drive back to. So let's bring it together. Zero Trust throws out the safe inside assumption and verifies every request, every time. Microsegmentation walls the network into zones to stop lateral movement, and an air gap goes further with total isolation. Trust but verify is the outdated model, and today the answer is zero trust. Privacy by design bakes protection in from the start, and Secure Access Service Edge delivers zero trust security from the cloud, right at the edge. Together, these move trust from the network boundary to the identity itself. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 8.2. This is the 64th session of the CISSP Exam Prep series. In this session, we'll look at the low-level techniques that keep programs honest. We'll answer several questions. What is confinement, and how does it box a process in? What are bounds, and who enforces them? How does isolation stop one crash from spreading? How do access controls decide who touches what? And what is the difference between trust and assurance? Why does this matter beyond the exam? Because a single misbehaving process can undo months of policy work. Imagine a document converter that runs on your servers, quietly processing files uploaded by strangers. If that process can wander into memory it should never touch, one malicious file becomes a full compromise. Knowing these techniques is how you reason about running risky code safely, which is a very common real-world problem. So what is confinement? And how does it box a process in? Confinement restricts what a process is allowed to do, letting it read from and write to only the memory and resources it was granted. You will also hear this called sandboxing. It is simply the principle of least privilege applied to a running program, and its goal is to stop data from leaking to places it should never reach. If a process reaches beyond its authority, the request is denied, the attempt may be logged, and the offender is often shut down. Think of a toddler in a playpen. They can play freely inside, but they cannot wander into the kitchen. What are bounds, and who enforces them? Bounds are the specific limits on which memory addresses and resources a process may touch. Every process gets an authority level, often as simple as ordinary user or privileged kernel, and that level sets its bounds. In most systems, memory is carved into logical segments, one per process, and the operating system enforces those lines and blocks trespassing. Stricter systems go further with physical bounds, giving each process its own physically separate region of memory. That is more secure but also more expensive. Picture assigned seats in a theatre. Logical bounds are painted lines on one long bench, while physical bounds are separate chairs bolted apart. How does isolation stop one crash from spreading? Isolation is what you get when those bounds are actually enforced. An isolated process can only affect its own memory and resources, so its behavior cannot reach out and disturb anything else. This protects the operating system kernel and every other application from a single misbehaving program. It also enables a fail-soft environment where one process can crash without dragging the others down with it. Confinement is the goal, bounds are the limits, and isolation is the result of enforcing those limits. Think of soundproof recording booths. A drummer can pound away in one without bleeding into the singer's take next door. How do access controls decide who touches what? Access controls limit which objects a subject may reach and what it may do with them. Access rules spell out which objects are valid for each subject, and even then, an object might allow one kind of action while forbidding another. Someone may read a file but not delete it. There are several flavors, including discretionary, role-based, and mandatory, which we explore in depth elsewhere in the series. Think of a hotel keycard. It opens your own room and the gym, but not the manager's office or another guest's door. What is the difference between trust and assurance? These two words sound alike, but mean very different things on the exam. Trust is the presence of a security mechanism. A trusted system has protection features that work together to handle sensitive data while staying stable and secure. Assurance is the level of confidence that those features actually deliver the security they promise. Here is the key point. Assurance is not permanent. Any significant change, a vendor patch, a fresh exploit, or simply the passage of time can erode it, so it must be continually re-verified. That is why change, patch, and configuration management matter so much. Think of a car. Trust is that it has brakes and airbags. Assurance is the inspection that proves they still work today. So let's bring it together. Confinement boxes a process into only the resources it was granted. Bounds are the limits the operating system enforces, and isolation is the result, keeping one crash from spreading to the rest. Access controls decide which subjects may touch which objects and in what way. And trust is having a security mechanism, while assurance is the ongoing confidence that it truly works. Together, these techniques keep the confidentiality, integrity, and availability of your data intact. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 8.3, Part 1. This is the 65th session of the CISSP Exam Prep series. In this session, we'll turn security policy into rules a machine can actually enforce. We'll answer several questions. What is a security model, and why do we need one? How do we tag an object's security attributes? What is the trusted computing base, and where is its boundary? What is a reference monitor, and how does the security kernel enforce it? What is the state machine model? How does the information flow model work, and how does non-interference stop hidden leaks? Why does this matter beyond the exam? Because a policy written in plain English cannot defend anything by itself. Someone has to translate no read up into logic a system can enforce 1,000,000 times a second. Picture an architect handing a builder a rough sketch. Without precise blueprints, the crew is guessing. Security models are those blueprints, and understanding them lets you evaluate whether a system genuinely enforces the policy it claims to. So what is a security model, and why do we need one? A security model is a formal way to express a security policy as explicit rules a computer can follow. It takes abstract goals and maps them into the algorithms and data structures needed to build the actual hardware and software. In short, it turns intent into something testable. It gives designers a yardstick to measure their implementation against. Think of a recipe. The vague wish to bake a good cake becomes exact steps and measurements that anyone can follow and check. How do we tag an object's security attributes? There are 3 common ways to describe what protection an object needs. A security token is a small separate object that travels with a resource and carries its security details, announcing them before access is requested. A capabilities list instead keeps a row of security attributes for each object, and while it is less flexible than a token, it offers faster lookups. A security label is usually a permanent, unchangeable part of the object it is attached to, and that permanence is its strength, because it resists tampering in a way the other 2 cannot. Think of shipping a package. A token is a removable tag, a capabilities list is the courier's master manifest, and a label is ink stamped straight onto the box. What is the trusted computing base, and where is its boundary? The trusted computing base is the combination of hardware, software, and controls that together enforce your security policy. It is only a subset of the whole system, and you want it as small as possible so it can be analyzed thoroughly and trusted completely. Around it sits the security perimeter, an imaginary boundary separating the trusted core from everything else. For the core to talk to the rest of the system safely, it uses tightly controlled, trusted paths, so no insecure communication crosses the line. Think of a bank vault inside a branch. The vault is the trusted base, its wall is the perimeter, and the single guarded door is the trusted path. What is a reference monitor, and how does the security kernel enforce it? The reference monitor is the part of the trusted base that checks every access request before it is allowed. It stands between every subject and every object, verifying that the requester's credentials satisfy the object's requirements. It is a concept, a rule, that must always hold. The security kernel is the actual collection of hardware and software that puts that concept into practice. The kernel mediates every resource request, granting only those that match the rules, and it is built to resist known attacks. Think of a nightclub. The reference monitor is the strict policy that everyone gets checked, and the security kernel is the bouncer who actually enforces it at the door. What is the state machine model? It describes a system that stays secure no matter what state it is in. A state is simply a snapshot of the system at one moment, and if that snapshot satisfies the security policy, the state is secure. The system changes state through transitions, which happen when it takes input or produces output. The rule is strict. If every possible transition leads from one secure state to another secure state, you have a secure state machine. Such a system boots secure, stays secure through every change, and never allows an unsafe step. Many other models build on this foundation. Think of a chess game where every legal move only ever leads to another legal position. You can never reach an illegal board. How does the information flow model work? It focuses on controlling how information moves, and it is built on top of the state machine model. It governs flow between subjects and objects, whether they sit at the same classification level or different ones, which is why it underpins multi-level security. The rule is clean. Allow every authorized flow and block every unauthorized one. It also cares about the direction and type of flow, and it can even describe how one object transforms from an earlier state into a later one over time. Crucially, it closes off covert channels by forbidding any flow path that was not explicitly defined. Think of a building's plumbing, where water may travel only through approved pipes and never seep through the walls. How does non-interference stop hidden leaks? Non-interference builds loosely on information flow, but it asks a sharper question. It makes sure the actions of a high-level subject never affect what a low-level subject sees or does. If a high user's activity could ripple down and change the low user's view, that low user might infer secrets they were never cleared for. That subtle leakage is exactly what a covert channel exploits. By forbidding that interference, the model also blocks a class of malicious programs, like a Trojan horse trying to signal secrets downward. On a related note, composition theories describe how systems chain together, whether one feeds the next, they feed each other back and forth, or one also leaks its input to an outside party. Think of soundproofing between floors, so the meeting upstairs never leaks a word to the lobby below. So let's bring it together. A security model turns policy into enforceable rules, and objects carry their attributes through tokens, capabilities, lists, or permanent labels. The trusted computing base is the small, trusted core inside a security perimeter, and the reference monitor, enforced by the security kernel, checks every single access. The state machine model keeps the system secure across every transition. The information flow model permits only authorized flows, and non-interference stops high activity from leaking down to low. These are the foundations, and the named models in the next part all build on them. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 8.3, Part 2. This is the 66th session of the CISSP Exam Prep series. This part moves from the foundations into the named security models. In this session, we'll dig into the classic models the exam loves to test. We'll answer several questions. How does the take grant model pass rights around? What is an access control matrix? How do ACLs and capability lists differ? How does Bell-LaPadula protect confidentiality? And how does Bieber flip that same idea to protect integrity? Why does this matter beyond the exam? Because these models are the DNA behind real access control systems you configure every week. When you set a file permission, inherit rights from a group, or classify a document, you are living inside one of these frameworks, whether you name it or not. Knowing the models lets you predict how a system will behave and lets you answer those tricky read up and write down questions without second guessing. So how does the take grant model pass rights around? It uses a directed graph to describe how permissions travel between subjects and objects, governed by 4 rules. The take rule lets a subject take rights from another entity. The grant rule lets a subject hand its rights to another. The create rule lets a subject generate brand new rights, and the remove rule lets it delete rights it holds. Together, these let you trace exactly when rights can change and where leakage might occur. You already see this in modern systems. When a user inherits permissions from a group, or a file inherits its access settings from a parent folder. Think of a set of keys. You can copy one for a colleague, take one that was offered to you, cut a new one, or throw an old one away. What is an access control matrix, and how do ACLs and capability lists differ? An access control matrix is a grid mapping subjects against objects, laying out precisely which operations each subject is permitted on each object. Read it one way and you get 2 different structures. Reading down a column gives you an access control list, which is tied to an object and names every subject's allowed actions on it. Reading across a row gives you a capability list, which is tied to a subject and names every object it can touch. That distinction matters for administration. Managing by object through ACLs is far easier than managing by subject, because revoking access to one resource through capability lists means editing every single user who had it. Think of a spreadsheet of who can enter which rooms. Columns describe each room's allowed people, rows describe each person's allowed rooms. How does Bell-LaPadula protect confidentiality? It was built for military-style, multi-level security, and it has one job: keeping secrets from leaking downward. It rests on a state machine, uses mandatory access controls, and arranges classifications in a lattice. Its 2 famous rules are the heart of it. The simple security property says no read-up, so you cannot read data above your clearance. The star property says no write-down, so you cannot copy sensitive data to a lower level, which would be like pasting a top-secret memo into a public file. A third property uses an access matrix to enforce need to know. There is one exception. A trusted subject may violate no write-down to legitimately declassify information. Remember, simple is about reading. Star is about writing. How does Bieber flip that same idea to protect integrity? Bieber came after Bell-LaPadula and is essentially its mirror image, swapping confidentiality for integrity. It too rests on a state machine, information flow, and multiple levels. Its rules invert the earlier ones. The simple integrity property says no read down, so you do not pull in data of lower integrity. The star integrity property says no write up, so you cannot corrupt data held at a higher integrity level. An invocation property blocks a lower process from requesting higher access. Keep the pattern straight. Simple always concerns reading, star always concerns writing, and each rule states what you must not do. Think of a pristine kitchen. You never let ingredients from a questionable source flow up into the dish you are certifying as clean. So let's bring it together. The take-grant model uses take, grant, create, and remove rules to move rights around a graph. An access control matrix reads as object-focused ACLs down its columns and subject-focused capability lists across its rows. Bell LaPadula guards confidentiality with no read-up and no write-down, while Bieber inverts that to guard integrity with no read-down and no write-up. Anchor yourself with one memory trick. Simple is reading, star is writing, and the rules always say what not to do. In the next part, we finish with Clark Wilson and Brewer and Nash. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 8.3, Part 3. This is the 67th session of the CISSP Exam Prep series. This part completes our tour of the classic security models. In this session, we'll finish the model family and clear up a word that trips people up. We'll answer several questions. Why does Bieber forbid reading down? What are Bieber's known weaknesses? How does Clark Wilson enforce integrity differently? How does the Brewer and Nash model handle conflicts of interest? And what does the word star actually mean across security topics? Why does this matter beyond the exam? Because integrity is not just about blocking outsiders, it is about not letting bad data poison good data. On the job, you constantly decide which sources are trustworthy enough to feed a validated system, and which commercial application should sit between a user and a database. These models give you the vocabulary to defend those design choices in an audit or a review. So why does Bieber forbid reading down? The no write-up rule feels obvious, since you clearly do not want low-integrity data corrupting a high-integrity object. The read-down rule is the one that needs a moment. Think of integrity levels like the cleanliness of air. You would never pump air from a dusty workshop into a sterile clean room. In the same way, you never let unvalidated, lower-integrity data flow up into a document you trust, because the risk of contamination is simply too high. That is why reading down is blocked. What are Bieber's known weaknesses? It is a useful model, but it has real limits worth remembering. It addresses only integrity, ignoring confidentiality and availability entirely. It focuses on external threats and simply assumes internal threats are handled elsewhere in the code. It does not manage access control, and it offers no way to assign or change the classification of a subject or object. And like several of its peers, it does nothing to stop covert channels. Think of a lock that secures your front door beautifully, but leaves the windows completely unaddressed. It is strong at one job and silent on the rest. How does Clark Wilson enforce integrity differently? Instead of a formal state machine, Clark Wilson protects integrity through a three-part relationship. The access control triplet of subject, program, and object. The key idea is that subjects never touch objects directly. They must go through a well-formed transaction, a control program that limits exactly what can be done. Protected data is a constrained data item. Unvalidated data is unconstrained. A verification procedure confirms integrity, and only transformation procedures may modify protected data. That constrained interface, plus separation of duties, is what keeps data trustworthy, which is why this model is so popular in commercial applications. Think of a bank teller window. You never reach into the vault yourself. You make your request through the teller, who is only allowed to perform specific approved actions. How does the Brewer and Nash model handle conflicts of interest? This model changes a user's permissions dynamically based on what they have already accessed. It is designed to prevent conflicts of interest inside a shared dataset. Imagine a consultant who opens files for one client. The moment they do, the model automatically walls off access to any competing client's data in the same conflict class. Once that task is finished, their broad access returns. The whole point is to stop someone from sitting on both sides of a rivalry at once. You may hear this called the ethical wall model. Think of an accountant who, the instant they start auditing one supermarket chain, is locked out of a direct competitor's books until the job is done. What does the word STAR actually mean across security topics? Here the exam sets a small trap, because STAR shows up in several unrelated places. First, there is no formal model literally called the STAR model in security, despite how it sounds. What does exist is the STAR property, the right rule inside both Bell Lapadula and Biber that we have already covered. Separately, a well-known cloud alliance runs a program abbreviated STAR that focuses on assessing cloud provider security through auditing and transparency, which has nothing to do with read and write rules. And in business management, there is an entirely unrelated organizational design framework that also uses the word STAR. Think of a common word like spring, which means a coil, a season, and a water source depending on context. Read carefully and let the surrounding words tell you which STAR is meant. So let's bring it together. Biber blocks reading down to keep low-integrity data from contaminating trusted data, though it covers only integrity and ignores covert channels. Clark-Wilson protects integrity through the subject-program-object triplet, forcing all access through controlled transactions. Brewer and Nash dynamically walls off conflicting data to prevent conflicts of interest. And the word STAR means different things in different places, so context is everything. With these models in hand, you can read almost any model question and know exactly what it is testing. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 8.4. This is the 68th session of the CISSP Exam Prep series. In this session, we'll learn how buyers judge whether a system is actually secure enough. We'll answer several questions. Why do organizations demand formal security evaluations? What is the common criteria? How do protection profiles and security targets fit together? What do the evaluation assurance levels measure? What can the common criteria not do? And what is an authorization to operate? Why does this matter beyond the exam? Because at some point you will help choose a product for a high-stakes environment, and marketing claims alone will not cut it. Picture a central bank shopping for a system to guard transaction records worth billions. They cannot simply trust a vendor brochure. They need independent proof. Understanding evaluation frameworks lets you compare products on evidence, not promises, and lets you sign off on a system with real confidence. So why do organizations demand formal security evaluations? Because some data is too valuable or too dangerous to protect on faith. Buyers of sensitive systems like national security agencies or major financial firms want to understand a product's strengths and weaknesses before they ever purchase it. So they insist on systems that have passed a formal evaluation and earned a security rating. Usually a trusted independent third party performs that testing, and their seal of approval is the real prize. Think of a restaurant that will only buy from suppliers with an independent food safety certificate. The certificate, not the sales pitch, is what earns the order. What is the common criteria? It is an internationally recognized framework that defines standardized levels for testing and confirming a system's security capabilities. It was designed to be dynamic and flexible, and it replaced older, more rigid rating systems that came before it. It is now published as an international standard, adopted by many countries so that one nation's evaluation is honoured by the others, which avoids wasteful duplicate testing. Its goals are to boost buyer confidence, keep evaluations consistent and cost-effective, and assess both what a system does and how much you can trust it. But an important caution stays true. Even the highest rating never guarantees a system is flawless. Think of a crash test rating for a car. It is a rigorous, shared standard, but a top score still does not promise you will never be in an accident. How do protection profiles and security targets fit together? These are the two halves of the common criteria conversation. A protection profile is the customer's wish list, the I want. It states the security requirements the buyer needs from the product being evaluated. A security target is the vendor's answer, the I will provide. It states the security claims actually built into their system. Vendors can also offer optional packages, extra bundles of security features, much like trim options when buying a car. The buyer then matches their protection profile against the security targets on offer and picks the closest fit. Think of house hunting with a must-have list, then comparing it against what each listing actually delivers. What do the evaluation assurance levels measure? Evaluation assurance levels, running from 1 up to 7, grade how rigorously a system was tested and verified. A low level means only basic confidence, suitable when threats are not serious, like light, functional testing. As you climb, the engineering discipline deepens, from methodically tested to methodically designed and reviewed to semi-formally verified. The very top level demands formal, mathematically rigorous analysis and is reserved for the highest risk situations guarding the most valuable assets. These levels give buyers a standardized way to compare vendors on trustworthiness. Think of belt ranks in martial arts. A higher belt reflects deeper, more rigorously proven skill, not just more time spent. What can the common criteria not do? It is powerful, but it has clear blind spots you must respect. It says nothing about whether users handle data safely once they have it. It ignores administrative matters outside its narrow security scope. It does not evaluate a system in its real setting, so it skips personnel practices, organizational procedures, and physical security entirely. It also does not cover control of electromagnetic emissions or rate the strength of cryptographic algorithms. Think of a certificate that proves a safe is well built, while saying nothing about who holds the combination or which room the safe sits in. The rating covers the box, not the whole environment. What is an authorization to operate? An authorization to operate is the official green light to run a secured system for real work and to formally accept its risk. It comes from the risk management framework, and it is the modern replacement for the older idea of accreditation. The decision is made by an authorizing official, a person empowered to weigh a system, its operations, and its risks. That official can issue 4 kinds of decisions: a full authorization to operate when risk is acceptable, a common control authorization when a control is safely inherited from another provider, an authorization to use when a third-party service, like a cloud provider, carries acceptable risk, and a denial when the risk is simply too high. An authorization is not forever. It must be renewed when it expires, after a significant breach, or after a major security change. Think of a restaurant health permit, granted when the kitchen passes, but pulled and re-earned after a serious violation or a big remodel. So, let's bring it together. Organizations demand formal evaluations because high-value data cannot rest on vendor promises. The common criteria is the shared international framework that rates a system's security, using protection profiles as the buyer's wish list and security targets as the vendor's answer. Evaluation assurance levels 1 through 7 grade how rigorously that security was proven, though the framework ignores users, physical setting, and crypto strength. And an authorization to operate is the formal approval from an authorizing official to run a system and accept its risk. Together, these turn security into something you can compare and defend. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 8.5. This is the 69th session of the CISSP Exam Prep series. In this session, we'll survey the built-in security features of information systems. We'll answer several questions. What does memory protection do? How does virtualization help security? What is a trusted platform module? What is a secure enclave? What is a constrained interface? What is fault tolerance? What role does encryption play? And how do you manage a system across its whole life cycle? Why does this matter beyond the exam? Because you cannot evaluate a platform you do not understand. Imagine you are choosing hardware to protect encryption keys for a payment service. If you cannot tell a chip that guards keys from one that merely stores files, you cannot judge the design. Knowing these capabilities lets you match the right protection to the right risk and lets you spot when a vendor is missing something essential. So what does memory protection do? It stops a running process from touching memory that was never assigned to it. This has to be built into the operating system and enforced no matter what program is running. Without it, you invite instability, broken integrity, denial of service, and data disclosure. It is the low-level fence that keeps one program from reading or trampling another's working space. Think of assigned lockers in a gym. Your key opens only your locker, and you cannot rummage through anyone else's. How does virtualization help security? Virtualization lets you run one or more operating systems inside the memory of a single physical host. Beyond squeezing more from your hardware, it is a genuine security tool. You can isolate operating systems from each other, and you can detonate suspicious software inside a throwaway virtual machine without risking the real host. If the guest gets infected, you simply delete it. Think of a bomb disposal containment chamber. You examine the dangerous item safely inside a sealed box, and if it goes off, the blast stays contained. What is a trusted platform module? A trusted platform module is a dedicated cryptographic chip on the system board used to generate, store, and process encryption keys in hardware. It commonly anchors full disk encryption, keeping the keys off the general storage where malware could grab them. It is one example of a broader category called a hardware security module, a dedicated crypto processor that manages keys, speeds up cryptographic operations, and includes tamper protection so it resists misuse, even if someone gets physical access. Think of a hotel safe bolted into the wall of your room. It guards your valuables right where you need them, and it is built to resist being pried open. What is a secure enclave? A secure enclave is a hardware-protected region that isolates code and data so completely that even the operating system, the hypervisor, and other privileged processes cannot peek inside. That extreme isolation makes it ideal for guarding the crown jewels, like cryptographic keys and, increasingly, valuable artificial intelligence assets such as proprietary model weights and training data. By running sensitive workloads inside the enclave, you keep them confidential and tamper-proof, even if the surrounding system is compromised. Think of a sealed clean room within a factory, where the most sensitive work happens behind a barrier that even the plant managers cannot cross. What is a constrained interface? A constrained interface limits what a user can see or do based on their privileges. A full privileged user gets every capability, while a restricted user gets only a slice. Applications enforce this in two common ways. They may hide an option entirely when you lack permission, so it never appears on your menu. Or they may show it but grey it out, visible yet unusable. Either way, the goal is to restrict the actions of authorized and unauthorized users alike, and it is a practical, everyday implementation of the Clark-Wilson model. Think of a self-checkout screen where the void item button is simply missing until a supervisor taps their card. What is fault tolerance? Fault tolerance is a system's ability to suffer a failure and keep running. You achieve it by adding redundant components, like extra drives in a redundant array of independent disks or extra servers in a failover cluster. It is a core part of avoiding single points of failure and building in redundancy, which is why it sits at the heart of resilient security design. Think of a commercial aircraft with multiple engines. Lose one, and the plane still flies safely to its destination. What role does encryption play? Encryption is the workhorse that turns readable plaintext into scrambled ciphertext, and decryption reverses it. Using both symmetric and asymmetric methods, it protects confidentiality by hiding data from prying eyes, and it supports integrity by proving data has not been altered. It underpins a huge share of the security solutions you will ever deploy. Think of a locked diplomatic pouch. Only the party with the right key can read what is inside, and any tampering shows. How do you manage a system across its whole life cycle? Security is not a one-time event. It runs from cradle to grave through 9 stages. You begin by gathering stakeholder needs, then analyze those requirements in detail. Next comes architectural design, the blueprint, followed by development where the system is actually built. Then you integrate the pieces so they work as a whole, and run verification and validation to confirm it meets its goals. After that is transition and deployment into live use. Then the long stretch of operations and maintenance, where you monitor, patch, and sustain it. Finally comes retirement and disposal, where you decommission cleanly, dispose of data safely, and stay compliant. Think of owning a car, from choosing it and driving it, through servicing it, to responsibly scrapping it at the end. Security belongs in every stage. So let's bring it together. Memory protection fences off each process. Virtualization isolates and contains risk, and hardware like a trusted platform module and a secure enclave guards, keys, and sensitive workloads at the deepest level. Constrained interfaces limit what each user can do, fault tolerance keeps systems running through failures, and encryption protects confidentiality and integrity everywhere. And you weave security through all 9 lifecycle stages, from gathering needs to secure disposal. Understand these capabilities, and you can evaluate any system with a clear eye. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.